Hello there. Today we're going to start chapter 11, which is the last chapter that we do in the class. And it's going to be a big departure from what you've seen so far. Most of what we do doesn't even look like calculus till much later in chapter 11. So it's a lot of sections that we cover here, and let's get started. So here's a quick roadmap of what we're getting into. Essentially, everything you've studied, starting with pre-calculus, or even college algebra, algebra 2, something like that, the functions usually are defined on an interval. But we're not doing that anymore for the rest of chapter 11. It's just a new way of looking at things. What we do instead is we study sequences of numbers, and it's just a function who takes every natural number and turns it into a different number. So it's a function from the natural numbers to the real numbers. Then we're going to look at an infinite series, so that's the sum of these numbers. So the first two sections that we do in chapter 11 are very, very different than a lot of things you've seen before. And one of the reasons we're really interested in this stuff is because, well, I mean, Isaac Newton first noticed it, because you can convert functions into these series, which allows you to do integration and differentiation, whereas you wouldn't normally be able to do it. So it's sort of a reworking of how we think of functions. And then the last section, 11:10, we're going to see that we're able to integrate functions that we have been unable to find antiderivatives for. So we're actually going to crack the code, so to speak, of more complicated functions. And it turns out that many of the functions that arise naturally in physics, chemistry, for those of you who are going to be engineers, you'll see these Bessel functions. They're defined only as sums. And so this is really, sort of like the capstone of all the work that you've put in your math classes. Takes you up to this point. All right, so let's see what a sequence is. So we've already seen in calculus so far that there's a lot of lists of numbers that result from applying a process in stages. So if you recall Newton's method from Calc 1, Newton's method used derivatives to approximate where a function crosses the x-axis. And every estimate gets a little bit closer and a little bit closer until you're just as close as you like. So that's just one example. And then the other example is something we're actually going to look at, that there's something called Zeno's paradox. Now, there was lots of paradoxes. He had 4 of them. But we're going to look at one of them. And Zeno, philosopher, he had a strange way of looking at things. And one of them actually is sort of what we're going to see in calculus. So in one of his paradoxes, Zeno argued that a man standing in a room could never walk to a wall because he would have to walk half the distance to the wall, then half the remaining distance, then half again. And according to Zeno, if you're always just getting a little bit closer, half closer, half closer, half closer, you could never actually get to your goal because you could never exceed that cutting in half. Right? And so you get a sequence like this. So how is it that you ever reach the wall if you're always cutting things in half? And it has to do with how they thought of things back then versus how we think of them now. But it turns out that this is a sequence. So the sequences we're going to see are infinite sequences. It's just a list of numbers written in some sort of order. That's all it is. So the first term is called A1, A2, A3, so it's second term, third term, and then the nth term. And every term has a successor. So every term has something after it. And so, for every number n, there's a corresponding A sub n here. And so the sequence can be defined as a function whose domain is the set of positive integers. So it takes all the positive integers and sends them to some real number. Technically, they could be a complex number, but we're not going to see that. And then there's lots of notation. Sometimes we just write an. Sometimes we write it in braces. Sometimes we write it in braces with the like the summation limits on it. And there's lots of ways to denote the sequence itself. So don't worry about, trying to get the notation precise. As long as you can read it, you're going to be fine. So let's find the first 5 terms in each sequence. So here we have a sequence that's defined by the an term. And here's one where we're given the first term and then each subsequent term. So this is the 2 main ways that we define sequences. Okay, so we're going from 1 to 5. So we just plug in 1, plug in 2, plug in 3, plug in 4, plug in 5. Simplify as much as you can. Now we have to do one more step of simplification because each of these numbers in the numerator also appears in its own denominator because of how the factorial function works. So we can actually further simplify this to this. Now, one thing we're going to have to do in this class later especially, not so much early on, but as we progress through chapter 11, is maybe go the other direction. We might be given this and have to work backwards to this. We're going to do it a little bit in this section, but it comes up a lot more later. So it's a lot of just numbers, and there's a lot of theorems, a lot of numbers, a lot of, I guess you could call it some algebra, but not so much. At least not in 11.1. All right, now the second sequence, we were given that A1 is 5, and then we were given what happens for each subsequent term. So A2 is 5 times A1 minus 4. So all you do is you take the previous term and plug it in here. So you get 21. And the next one, A3, will be 5 times 21 minus 4. And you just keep going like that. Then we plug in 101. We plug in 501. And then we stop. So these are just a couple examples of how we carry out finding sequences. And we do a lot of work with sequences in chapter 11. So you're going to get lots of practice today with this video and the homework. Now we're going to go the other direction. We're starting with the sequence, and then we have to work backwards into the pattern. All right, so let's start with the first one here. So I'm just going to give you some idea of just realistically what you can expect in chapter 11. Many of these patterns will not just jump out at you. You've got to really look carefully at them and really think about it. So for example, just look for things that'll tip you off as to the pattern. So notice we have a negative, positive, negative, positive, negative. Well, anytime there's a sign that anytime there's a sign change every term, that means somewhere there's a factor of -1 to the n or -1 to the n plus 1. Here we're starting with the negative. So when n is 1, -1 to the first is -1. So there's going to be something times -1 here. And then you just look for other patterns. In the numerator, we can see this is 2 to the 5th. And this is the 5th term. So it's believable that there's a 2 to the n somewhere here, right? So 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 squared, 2 to the 1st. So -6 has a 2 in it. So there's going to be a 2 to the n. But this denominator's funny, right? This is 3 to the 3rd, not 3 to the 5th. And this is 3 squared, and this is 3 to the 1st. So 3 to the 3rd, 3 squared, 3 to the 1st. Technically, this is a 3 to the 0. And then if you do one more step and say, well, we already have a negative over here. We already have a 2 over here. What if this is divided by 3 to the -1? That would be the same as multiplying by 3, which would give us our negative 6. So there's a 3 to the n minus 2. So it looks like this. And if you go through and just plug all the numbers in, you see that it works. So if we plug in n equals 1, we get negative 2 divided by 3 to the minus 1. So dividing by the third is the same as multiplying by 3. We get negative 6. And you can try all the other n's, and you'll see that you get the entire sequence. But this is not considered simplified. It is in some sense, but what we're going to see in the next section is that you want it to look like this. It might not be clear right now why that's true. But given a choice, you want to arrange this thing in such a way that you have a number to a power. So one number to a power. And then anything else that is not that number to that power gets multiplied. You just pull it out to the front. So I know that's a little funny, but that's how it's done. Now, if you did this on a test, this would be fine. But putting it in this form is going to help us solve problems later. So all you have to do is just arrange some stuff. It's not hard to do the algebra from here to here. All right, let's look at the next one. 10, 0, 10, 0, 10. So it just keeps alternating tens and zeros. Well, it turns out there's lots of correct answers for this, so I'm going to list 2 of them. This is the first one I found. Right? So if you plug in n equals 1, right? Sine of, so pi times 1 over 2. So sine of pi over 2 is 1. 1 squared is 1 times 10 is 10. When n is 2, you get 2 pi over 2. Sine of pi is 0. So 0 squared is 0. 10 times 0 is 0. Then you plug in 3. You get 3 pi over 2. 3 pi over 2 is negative 1. Right? Sine of 3 pi over 2 is negative 1. But we square it to make it 1 and multiply by 10. And the pattern repeats from there. So you can see that that definitely works. Here's another way to do it. So if n is 1, negative 1 squared is 1. 5 plus 5 is 10. But when n is even, this is odd, and this becomes a negative 1, and you get 5 minus 5, which is 0. So this just alternates plus 5 minus 5. So 2 very different ways to do it, but both correct answers. Again, we're going to do a lot more work with this kind of stuff later on in Chapter 11. For right now, you just really have to be able to see that the answer works and why it works, as opposed to coming up with your own. We're going to spend plenty of time coming up with our own answers later, when the problems get more complicated. All right, many of the sequences we will see have a defining equation called a closed form, but not every sequence has a closed form. So here's an example of one that if we just let an represent the nth decimal place of the number pi, you just get a list of digits. It never repeats, there's no pattern, and there's certainly no closed form. And then here's another one. This is called the Fibonacci sequence, and this is what's called a recursively defined sequence, where you plug in the first 2 numbers, and then every other number depends on the 2 numbers before it, which is pretty interesting. All right, let's keep going. So we can graph sequences. We normally graph them just on an ordinary XY graph, but it's like the NAN graph, right? If you want to think of it as X and Y in your head, that's totally fine. But it's the NAN coordinate plane. And so, because a sequence is a function that sends natural numbers to discrete points, then we get, so the first, point would go to a1. So that's here, right? So our first, for this sequence, n over n plus 1, if you plug in 1, you get 1/2. So the point 1/1/2 gets plotted. Next one is 2/3. So the point 2/2. It's the second term in the n axis, and then its height gets plotted, and so on and so forth. And what we use graphs for is to learn about limits of sequences. So the main thing we're interested in, sort of in a general sense in Chapter 11, is if we continue the sequence indefinitely, does it converge to a number or does it diverge? So from this graph, it looks like it converges to 1. But let's prove it. So n over n plus 1 is the same as n plus 1 minus 1 over n plus 1. So I can just separate this into two different fractions, right? And I can take this limit. So this limit, maybe I don't want to do, but this one I certainly can do. Right? So the limit as n goes to infinity of n over n plus 1. It's really just this limit, which is really just this. And when we plug in infinity here, 1 divided by infinity is 0, so we just get 1. So this is one of many ways that we could prove this limit, right? But we're going to spend more time on that here in a sec. But this just to show you that the graph gives us information about what's really happening. And so when we use this notation, the limit as n approaches infinity of an equals L, it just means the terms of the sequence approach L as n becomes large. So it's really defined almost exactly the same way as limits at infinity were defined in Calc 1. It's not that much different. You just have to remember that these are not smooth functions. These are just collections of points. They're not connected. That's the only difference. So for our definition for a limit of a sequence, this sequence has the limit L, and we write limit as n approaches infinity of an equals L. If we can make the terms an as close to L as we like by taking n sufficiently large. If the limit exists, we say the sequence converges or is convergent to L. Otherwise, we say the sequence diverges or is divergent. So here are two different convergent sequences, right? In the first one, it just goes up and then slowly comes back down. In the second one, it kind of oscillates around but still gets closer. Okay, so that's, again, the intuitive definition, similar to what you did in Calc 1 when you first learned about limits. But there's a technical definition. We're not doing any proofs with the precise definition. But again, very similar to Calc 1. A sequence has the limit L, and we write limit as n approaches infinity of an equals L. If for every epsilon, there is a corresponding integer n such that if n is greater than that number, then the distance between an and L, right, so absolute value is distance, is less than epsilon. So what this basically says is that if you pick some little bit above and below L, that you can eventually go far enough to the right, whereas the an terms from that point and to the right never jump outside of the bounds. And that's for every epsilon. So, and that's how limits work. We're just saying there has to be some number somewhere sufficiently to the right. So, make sure you understand this definition. We build very heavily upon all of this information as we move forward. You cannot afford to get behind as we progress through, because we're going to pick up probably 6 to 8 new rules every class, like every video. So by the end of Chapter 11, we've probably got 50 new rules. So you got to keep up on these. Now, sequences can diverge in two different ways. You have oscillation, and then you have goes to infinity or negative infinity. That's really all that can happen. And as you recall, those are the same things we had when we did functions at infinity. not just sequences, same thing. So here's the precise definition of our infinite limit. So when we say infinite limit, we're talking about this divergent limit here. Here's the definition for positive infinity. There's the opposite one would be negative infinity. So I'm only going to do the definition for positive infinity. You can use your imagination to imagine what it would look like for negative infinity. So the notation limit as n approaches infinity of an equals infinity means that for every positive number m, there exists an integer n such that if lowercase n is greater than capital N, then an is greater than m. So that's very abstract, but here's how it works. It's just saying, so this is like what you'd think of as a y-coordinate, m. It's just saying that there's some number on the graph, some horizontal line on the graph, that if you go far enough to the right, the sequence goes above that and stays above it. That's all it's saying, right? If you are to the right of some number, then the height of the graph is above some different number. That's all it's saying. All right, now we're going to look at what happens when sequences converge. So the first thing we want to talk about is using functions of x to help us with functions of n. So that's what this is saying here. If this limit exists, and if plugging in n into the function gives you an, so we're just saying that as you progress through this function, if you take every integer coordinate, positive integer coordinate, you get your ans, then this limit equals this limit. What this is going to do is allow us to use a lot of substitution properties, because there's things we can't do with n's that we're going to be allowed to do with x's. A good example would be L'Hopital's rule. Right? L'Hopital's rule involves a derivative. You can't take a derivative on unless the function is continuous. Well, this function is not continuous. But if this one is, and we can plug it in, then the limit's the same. So what we'll do is we'll go do work in x and then come back to n and get our answers. So here's a good example. Since we know that the limit as x approaches infinity of 1 over x to the r equals 0 when r is positive, then this limit has to be the same when r is positive. Because what we're saying is plugging in n into this function is the same as plugging the n's into this function. And this one, we have derivatives, we have L'Hopital's rule, we have lots of stuff we can do. So we're just relying on what we already know about continuous functions when we're dealing with functions on the integers, like a sequence. All right, now we have our limit laws. So we pick up every limit law that we have from before in Calc 1, except there were 2 limit laws that we don't have. But we have L'Hopital's rule for both of those, so it's okay. So you're not going to have to do a lot of work with limit laws, but occasionally we do. So just make sure you know that your limit laws, make sure you know what you're allowed to do and what you're not allowed to do. Now we're going to look at theorems that deal only with convergent sequences. Right? Just to show you. Here we looked at divergent sequences. Here are some properties of convergent sequences. It's a theorem. Here's your limit laws. So notice these limit laws are using these properties, right? Because these properties involve n. But we've just said that if you have n's, you can go back and look at things that had corresponding x's. And the limit laws that we had earlier back in your Calc 1 class had x's for all these. So we're just saying that whatever properties you have when there's an x in there, you pick up the same property when there's an n. That's all we're saying. All right, so we have a squeeze theorem here. So we had a squeeze theorem when these were x's. So, of course, we have a squeeze theorem when they're n's. Right? So this is saying that, remember, these are the y-coordinates. right? So we're saying that if at every n, this is less than that, or equal, for n beyond some value, and the limits of the outside functions are equal, then the limit of the inside function has to be the same thing. And the graph makes that pretty clear, right? You can see that an and cn are coming together, and bn is trapped in the middle, and it gets squeezed into having the same limit. All right, here's two more theorems that we need, both for convergent sequences. Both of these might look kind of hard to use, but once you hear about them and think about them, I'll show you how to use them. So this is saying if the limit as n approaches infinity of the absolute value of a sequence is 0, then the limit of just the sequence itself is 0. So that should be easy to see why it's true, right? This is going to help us deal with alternating sequences. So take the absolute value, look and see if it goes to 0. If it does, then you can take off the absolute value. That's what it's saying. And clearly it goes the other way as well, right? If this is true, then this must be true too. All right. Now, this last theorem here. So this is saying that essentially we're allowed to plug in L if the function, so the underlying function, is continuous. Right? We talked earlier about, replacing n's with x's. This is saying that, we can just plug in the limit if the function is continuous at the limit. And this is a helpful property for doing some other stuff that we're going to do. Right? It basically says that we can replace an with L. Right? All right, let's do some work. So here are 6 examples. Well, it's one example, but 6 sub-examples. I tried to pick out just stuff that you're going to see in the homework here, stuff that's interesting, and stuff we're going to see in future sections. All right, let's look at the first one. So notice we have n's here, but remember what we used to do when these are x's. When you have rational functions, when these are x's, you divide by the highest power in the denominator. Well, that's what we're going to do. So the highest power in the denominator is n squared. So we divide each term by n squared. Right? So we get 5 over n squared. Dividing that by n squared gives us 6n. N over n squared is 1 over n. And 3n squared over n squared is 3. Now, we can use limit laws and push those limits up inside. This is going to be 0. This is going to be infinity. 0, and this is going to be 3. So we get infinity. Now, you can write the limits as infinity, or you can say dne, or you can say divergent. They all mean basically the same thing. Just like we had with limits when these were x's, the limit does not exist, but it fails to exist in a very specific way, right? This is an infinite limit, which we had in Calc 1. There's other kinds of limits that fail to exist, and we're going to see those as we go through. All right, what about this one? Well, this function's continuous, so we can just push the limit up inside the exponent and evaluate it directly. So this one was actually really easy. We didn't have to do much. But again, this is the type of thing we're going to be doing, right? All right, well, those two weren't too bad. Let's keep going. So here, if you try to plug in infinity, you get infinity times 0. So you should rewrite it like this. try to plug it in here, you get infinity over infinity. We need L'Hopital's rule for infinity over infinity. But we're not allowed to apply L'Hopital's rule directly because it only applies to real valued functions like things with x's. So what we do is we rewrite the n limit with x's instead. Now it's continuous, and we can do L'Hopital's rule. Plug in infinity, and you get 0. So that's a really nice way to do it. And we just proved that the limit of the function with n's instead of x's is the same number. So that's how you use theorem 11.1.4. Right? Replace n's with x's, do whatever calculus you need to do, put the n's back in, and the answer is the same. All right, let's look at part D. What about this sequence here? So this is just alternating, but it definitely doesn't converge, right? So this is a divergent sequence, but it's a special kind of divergent, right? It's not infinite, but it does diverge. So remember, we can have two different types of divergent. Infinite divergent or just oscillation. This is the oscillation part. And it doesn't need to oscillate regularly. It can be just a random oscillation. That's still oscillation, just so you know. This one just happens to be very nice and easy to figure out. All right, what about this guy? So we try plugging numbers in, and we get another indeterminate form, so it's L'Hopital's rule again. Because 1 to the infinity, we don't know what that is. You might think it's 1, but we don't know. Let's find out. So what we do here, this is a special algebra trick. We're going to set the inside of the limit with x's equal to y. So we're just calling this a function of y. Remember, we can do that. We can plot points on this function. Then you take the natural log of both sides. And when you take the natural log of both sides, you can pull this x to the front, like that. And now what we have is something that we can use L'Hopital's rule on. So y is equal to this. So we take the limit, natural log of y is equal to this. So we're allowed to tack on limits. It's a rule from Calc 1. When we tack this limit on here, I'm putting this x in the denominator because this is still indeterminate, right? This is infinity times 0, right? Natural log of 1 is 0. So it's infinity times 0. When you have infinity times 0, you have to put one of the functions in the denominator. So to me, it was a lot easier to put this x in the denominator and call it 1 over x. Now when we try to plug these numbers in, this is 0 divided by 0, which is a classic case where we can use L'Hopital's rule. So we go ahead and use L'Hopital's rule. Those derivatives are not hard to do. And look at what happens. Something nice happens. These cancel. Now we can plug in infinity and get 1. So what we have is natural log of y equals 1. Right? This is one long chain, right? Right, because we evaluated the limit here, so we dropped the limit on the left side too. Well, if natural log of y is 1, then y is e to the first, or just e. And that's the answer. So e is about 2.718. So this thing that looked 1 to the infinity power, is it 2.718? Turns out it's different every time you do it. You'll have some of these on the homework where this number is different, but it still looks like 1 to the infinity power, but each answer is different. So indeterminate forms have something in them that lets you sort of pick whatever you want the answer to be. So you want the answer to be e squared? Make that a 2. All right, let's keep going. We got one more. What about this guy? So if you plot this graph, you'll see it alternates, but it looks like it settles down at a limit. But you notice that there's that negative 1 to the n in there. That tells us we should use theorem 11.1.6. And in order to evaluate this limit, let's take the absolute value of it. So what you do is you just tack on an absolute value around the whole thing. Then you get rid of everything that absolute value washes away. So all the negatives are gone. Well, here you can see clearly this is the limit as n approaches infinity of 1 over square root of n. You plug in infinity, 1 over square root of infinity is still 0. So you're actually done. That's the end of the problem. Again, we used theorem 11.1.6, so make sure you know why the stuff is working when you're doing it. On a test, you're not going to be allowed to guess. You're going to have to give me good reasons why you do everything. There's only 3 theorems. There's only 3 theorems in this section that are not named. They just don't have special names, so make sure you know them. All right, almost done. Last thing we want to look at are monotonic sequences. So a sequence is called increasing if an is less than an plus 1. Well, that just means every subsequent term is larger. So it increases. It's the same definition as if these were x's. And it's decreasing if terms farther to the right are less than terms to the left. And if a sequence is increasing or decreasing, it's called monotonic. So you do have to know that term because it comes up a bunch. So here's a good example of a decreasing sequence, right? 1 over n. Because every term to the right is smaller than all the terms to the left. It's monotonic because, it just keeps going down size-wise. All right, let's do another one. Let's talk about bounded sequences. So a sequence is called bounded above if there's a number m such that an is less than m for all n greater than 1. This just means, again, that you can draw a horizontal line on the graph and the function will never exceed it. That's all it means. And bounded below means you can draw another horizontal line and the function will never drop below that. Right? The sequence will never drop below. And if it's bounded above and below, this is not or, this is and, then it's called a bounded sequence. So the reason we care about bounded sequences is going to be made more clear in future sections. But we definitely care about them. They help us solve problems, as you're going to see. So here's a bounded sequence, right? This is the one we saw in the previous slide. An equals 1 over n is bounded because it's always positive and it could be at most 1. So this is monotonic and bounded, right? It's actually decreasing. But be careful because not every bounded sequence is convergent. So negative 1 to the n, we saw that one earlier. It's definitely bounded by negative 1 and 1. But it oscillates, right? And monotonic sequences don't need to converge, right? So if we just list all the natural numbers, 1, 2, 3, 4, 5, all the way up, that definitely doesn't converge. It just keeps getting bigger and bigger and bigger. But we do have the monotonic sequence theorem that tells us every bounded monotonic sequence, in fact, is convergent. And the one we saw in the previous slide, 1 over n, is bounded, monotonic, and therefore it converges. So I'm not going to prove this. The proof is in the book if you're interested in it. It should be believable, though, right? Try to imagine a case where you have a monotonic sequence that's always increasing or always decreasing, and it's bounded, but somehow it diverges. Just Just try to imagine that. Like, how would it diverge if it's trapped between two boundaries, right? It would have to jump over one of the boundaries, which it's not allowed to do. So just think about it. Think about why this sequence theorem should be true, and I think it'll help you remember. All right, well, that's it. Next time we're going to look at series. And if you got any questions, let me know. And I'll see everybody next video. Bye-bye.